Hello everybody, welcome back to Rhubarb Shed. Tonight we're not going to be talking about this gearbox. But I just wanted to show it so that you can see that I am making some good progress with it. That's in the upcoming episode, and we've successfully welded it and I feel a lot better. We're still on the hunt for another one, but sometimes you've got to back two horses. And the first horse is welding and jig boring this casing, and we're making great progress, but I don't want to rush it just so I can get an episode out to you. So I'll show you something of the little side project I've been working on, and that's all to do with your lovely Smiths Chronometric clocks. The reason I'm talking about this is because this clock is off George, but unfortunately I got the wrong ratio at the wheel, and of course it doesn't give the right speed. But that got me into a conversation with a good friend of mine. What he said to me was that he was sure that you could buy digital Smiths clocks and they looked exactly like chronometrics, but he hasn't been able to find one on the internet. And of course this conversation was in his workshop, which is lovely, with my son in attendance. His need for the digital clock made my son pipe up, because he's a roboteer. He likes the robot wars, and he enters two robots into nationwide competitions. He's got a very interesting take on how to solve this problem. So with my 3D modelling and my 3D printing skills, it looked like the three of us were very well placed for bringing a small project like this in. I'll put it on my Patreon so that you can download the files and the software that we've developed, and you can print the pieces yourself. But essentially the whole point of this project is it's a very certain sort of proportion, the shell of the Smiths clock. The bezel is quite particular, the dial is so distinctive, and of course mounting points. The mounting points are on the centre line of the back face, and modern digital clocks somehow have, the input at the centre, so you can't even use your original Smiths brackets. All of that in mind, let me take you and show you how I modelled this, created a chassis for the servo and the teensy. More of that later. I hope you like my new sweatshirt. I got the feeling that the reason I had a disaster with the gearbox was because I was wearing a pesky Triumph sweatshirt all the time. So I've gone and addressed the clothing, the attire problem. Hopefully that'll lead to a bit more good luck in future. Anyway, let's go and get on with it. Here we are, sat in front of my computer. This is the assembly that I've done. Rudimentary rendition of the shell. Say rudimentary, I'm not interested in modelling this thread. I just want it the correct size, the nice radiuses, all of the holes in the correct position, the mounting studs, any features that are inside, like these weld bosses. And the idea is that once I've modelled that and the dial in position, I can then work out what size servo I can fit inside, where the little microcontroller, why can't I say that word? Microcontroller, where the microcontroller is going to go. So let me just disassemble this for you. I'll start by taking the dial out. And so now you can see inside there's a transparent 3D printed chassis, if you will, which is designed to hold this servo and this little circuit board here, and that's the microcontroller. So I've made provisions in there for wiring to go round between the two components. There's clearance for the wiring where it comes out at the end of the servo, and there's the original bulb holder, and the original position where the cable comes in, because we feel that that's where the input from the electronic ignition could come in, and you could even make that look like a real cable at that point. Because these cases are painted white inside, the idea of that is to reflect light around the inside of the casing, so you get this little edge of light of an evening when you're riding at night time. So that's the reason we've included this feature here, made the entire chassis out of a clear substance. I think we're going to go for PETG and see how that happens, see how that works. So I'll just turn the shell off and you can see the relationship between the components at the back side. Now, it's just a simple structure and it's all based on the features that you find inside the shell and the features that you find on the servo, and it's a case of sort of marrying those two ideas up, because what we want is the original look, even down to the way it's lit. We want it to look just like the real thing, but inside it's going to have the electronics, and the only real modification is that the dial needs a larger hole in the center for this spline to stick through. So let's get into it, shall we? I'll open the shell and show you how I modelled that. So here's the shell. It's just a very simple piece of modelling. I'll roll the model back because there's no need to go into it in too much detail. We start with this shape, which we've done by revolving this sketch. I'll edit the sketch. We'll go normal to it. So you can see that my measurements are in inches, which takes a little bit of getting used to for me. It's quite a simple shape. Two lines, basically, two parallel lines which follow each other round a radius in the corner. It's capped off at both ends, and then there's a centre line. What we do is we rotate that sketch around and it forms the solid which you see in front of us, which is the basic cup shape of the shell. So the next thing I modelled was these two bosses, which are the mounting studs. No need to go into too much detail, as long as they're the right size and position, and they are simply created with a sketch on this plane. Let's go normal to that one as well. I worked out what the centres were and what the diameters were, and I've constrained them on another centre line, which just makes sure that they are equidistant from the centre and they are vertically above each other. So let's rebuild that sketch. I still haven't modelled the inside bosses, the weld bosses that do have a bearing on the shape of the chassis, so I'll go into that once we've seen all the features. So the next feature is a series of cuts which represent these holes here, and of course it's just another sketch. Let's go normal to this one. It's quite elaborate when you measure somebody else's design. You have to reverse engineer what they've been thinking, and quite often you see nice round integers of measurement units. Well, of course we're working in inches because that was designed by somebody a long time ago. So I've got my verniers set to imperial, and I did a lot of measurements, and it's difficult when you've got features like these two holes which are obviously in line with each other symmetrically about this angled line, But what I found was, you almost imagine that the midpoint between these two circles is going to be on the midpoint or the center of the shell. In actual fact, it isn't. So you can, kid yourself on that you're understanding how somebody's designed something. Really, the only way to get it right is to measure. And so in the end, I created a little paper template just to be sure that I got them in the right place. So I'll just fit this on the shell and show you. I know you can't see what I'm doing there. Once you've transferred all of the features, you can even do a little bit of a brass rubbing if you like. You've got a piece of paper then, which is a little bit easier to lay flat on the table and measure. So that's how I've obtained all of these measurements. I've drawn them and used the cut feature to just throw them through those bottom surfaces. And finally, there's a small boss around the edge of the lighting ring, and there's not much more to say about that. It really didn't come into play, but somehow or other I thought it was necessary to model. So anyway, that's the first part, and then what you have to do is understand how the parts go together. So I'll show you the dial next. Okay, here we have the dial, and it's a very simple disc. You can see that the hole in the center, if you own one of these things, you'll know that the hole in the center is very small. It's about 1/10 of an inch, whereas the hole for this servo, as already described, is a little bit bigger, but we'll come into those details a little later on, because in order to fit this, we're going to have to drill out the hole in the center of the dial, and that'll become apparent when we come to fit it together. But for the purpose of this exercise, I need to now include the two holes that will mount the actual dial to the chassis. I'm thinking about putting little self-tappers through the bottom of the chassis, so I'm not going to specify any hole position in the design. It's just going to be open to interpretation, that. So it might be a way of just dealing with any, slight distortions, should we call them. We'll start a sketch on this surface. That's how you do that, with the little pop-up menu. I'll go normal to it, which is what I like to do when I'm working. Sketch tab, we'll create some center lines. So the first center line is going to be vertical. It goes to about there. The second center line will be a midpoint line for construction, and it means we could start in the center and that'll be equally disposed either side of that point. So a hole at each end of the center line. They're massive, aren't they? Look at that one. What we can do is we can give it a size. I'm just going to say 0.1, and then what I'm going to do is say this circle, and I'll hold shift down, and this circle are going to be equal in size. That's nice, isn't it? Green tick. So the next thing we need to do is measure our actual dial for the distance between centers. I'm just going to take an arbitrary figure of 0.1 of an inch, 1/10 of an inch, just for the sake of showing some holes in the dial. Measure the distance apart, so the centers of these two holes. So what I've done, I've got the diameter of the head. I'll zero the vernier, the digital caliper, and then I'll take a measurement from the outside of each head. Effectively what that does is it cancels out the diameter of the head and gives you the centers. So I've got 1.462 1.462. Let's put a dimension between centers. Oh, there it is. 1.462. It was pretty close, that, wasn't it? And now all we need to do is draw a line for guidance on the center of one of these holes. Just going to make it fixed to the edge. What I really want to do is line that up with the center of the dial. Just going to select that line, shift, select the center of the circle, and I can use this breadcrumb menu to make them coincident, so you'll see them snap into line with each other. And the idea of that is that when I've re-zeroed my caliper, I can literally take a measurement to the edge. 1795. We can click the line, okay, and we can bring out a dimension here. We can say 0.1795, but we know we've got to add half the diameter of that hole, which is 0.1, so plus 0.05, and then that'll give us the exact center line position to the edge of the dial. Now, does that look right? That's as near as damn it. And what we'll do is we'll create a feature which is an extruded cut, and we'll say through all. Right, there you are. Just for the sake of argument, we'll put the picture back in and see how close they are. The photograph is so badly scaled, but it shows they're in the ballpark, and we're going to drill these in position afterwards anyway, so it really won't matter if we're wrong. All this is going to show us is where those screws are going to come through the bottom face of the chassis. So without further ado, let's save that and go back to our assembly. I downloaded this servo, by the way, and I modelled the TNC4 and just slapped a photograph on it to represent what the pin positions would be like. Let's put the dial back in. Okay, you can see those two holes now, and we'll be able to see through from the back. Now, that's interesting, isn't it? We come very close to where we're going to hot glue this onto this surface. The actual position of that circuit board may require a little bit of packing, so we could alter the design to make that happen. But let's stop mucking about and get ourselves in a good viewport to looking at doing some edits. So it's the chassis we want to work on, so select that. We'll go into edit and we'll find the feature that we're looking for. It's that one there. When you click on a feature in the model, it can go down to the feature in the tree. You can edit the sketch, and I think it's this dimension here. You'll notice the schoolboy error straight away. So I tend to work in metric all of the time, so when I built the assembly, I was, at pains to measure everything in imperial on my caliper. But of course, when I'm designing something new, I just go back into metric mode. So that's exactly what I did. I measured all of this in millimeters, and so all I want to do is push the TNC away from that danger zone. So I'll change this to 5mm, update that, and when we rebuild it, we should see the little microcontroller move in relation. There we are. Because that is mated from that surface there, it will update and push it across. Oh, and you can see those holes are much further away. And there was one other feature that I needed to take care of, and that's these little bosses on the inside of the shell, which are going to impinge on this edge as I've designed it. So let's go to the shell. We'll start a sketch inside, normal to it. What we can do is change the transparency to hidden details, and then that means we can see the two studs that we're looking for as dotted lines, so we know where we're working. And what we've got here is some quite large diameter lumps, 0.6 of an inch. So we go to sketch and we'll draw some circles, and if we hover on that hidden detail we get a center point that we can snap to. Let's pop some circles, both of those. We'll give one of them a dimension and make them equal, 0.6 of an inch, and we'll make both of them equal. And then there's a straight cut on each one of them, which looks like, it doesn't have to be very accurate, this. Looks like it's just enough to clear the inside. So I'm going to give that a dimension of 0.2 perhaps. Yeah, that works. We have a little midpoint line there. We can mirror that about this. And a right click on the mouse is the same as a green ticky tick. And then trim the entities. So I'll just trim that bit off and that bit. What we can do now is we can extrude a boss or a base. I'm going to call that 0.1. So when we save that and go back to our assembly, we can turn the shell on, I can turn the dial off, and now we can see where that is impinging on the shape of the chassis. So I can do an in context cut and make clearance for that. Okay, so the last thing to do is make some clearance for those weld studs. The way we can do this is selecting the right plane, section, and in the feature tree, before we press green ticky tick, we can just click on the shell. Okay, and then we can say include this selected, and then all that does is it sections the shell and leaves everything else intact. So we can get a clear idea now of where the interference is occurring, and it's only just a tiny little bit. So what we'll do is we'll have a look at the right hand side, zoom in close, edit the chassis, and we'll put a sketch on the right plane of the chassis, and it can just be a little simple rectangle, and we can make it, I don't know, if we make it say 6-ish like that. Don't forget this is an arch going around here, so we need to take account of the chord of that circular cut. Okay, and we'll just go features and we'll do an extruded cut. I want you to notice here that because we're working in an assembly, all of the tools for the features have been slid across to the right, and there's some assembly sort of context tools to the left, and that just reminds you that you're modeling something in context, which is a nice little thing because you can get mixed up. All right then, so let's say extruded cut, and we want to go mid plane, and we'll say, should we say 7 mil each way, which I think we just put that figure in there as 14, and you can see there's a nice generous bit of clearance there now. Okay, that should be fine. Job finished. Save, and then we need to print it. So this is a program for interacting with the 3D printer, for creating something called G-code. And G-code is just a set of instructions for the 4 stepper motors that my printer has. So we've got an X, Y, Z, and a feed stepper which feeds the filament through the nozzle. And so what you do is you bring your model into this bit of software, open files, we're looking for chassis version 3. We really do want it the other way around. So I'm going to use the red circle to spin it over. When you get it to a certain point, you can lay it flat. We've got it set for my own version of PET-G, and we're going to slice it. Okay, won't take too long to do this. Basically cutting it up into layers, and the nozzle can go round and round, applying material. And you can see how the machine builds up each layer as it goes, and there's infill material and there's support material happening all at the same time. And finally we reach the top of the wall, and we just bring this spigot above, and that's great. So I'll save that to a removable disc when I've got it. So we'll get the printer started. It's a very nice one, that.
Beautiful.